Welcome to CS Colloquium for the spring semester. We're virtual to begin with. Probably when this wave settles down, we'll return to in-person, but though you'll still be able to join remotely. For today, I'm happy to introduce Brandon Booth. He's a postdoctoral research associate in the Emotive Computing Lab. His research focuses on multimodal machine learning techniques to model human behavior, perception, and experiences. He has a PhD from University of Southern California, industry background in video games, serious games, robots, computer vision, and human-computer interaction. Thanks a lot. Happy to have you. Take it away.
All right. Well, thank you very much for having me, and thanks for the introduction. So yeah, today I'll be talking about machine intelligence for naturalistic human behavior and experience modeling, which is a collection of different work in this broad field of human-centered computing. As was mentioned, I have a diverse background in industry. So I have worked in the video game industry, developing games where we're interested in optimizing games for entertainment value. I've worked in the hardware industry, building circuit boards for specific sorts of products designed to be used by people. I've worked on autonomous robots, where those robots are performing some task ultimately to help people perform some other task. And I've also worked on geospatial visualization systems. And what's unique about all of these systems is even though they have their own unique technical challenges that need to be addressed when you're constructing them, ultimately the success or the failure of all of these products is really determined by how people interact with them and how well they're able to help people. So over the years in my time in industry, I became really interested in this question. How do we actually optimize for human utility or human experience value? Because as we're all aware, people can have a wide range of emotions and maybe things are more or less useful in different contexts. So my research falls into the field of human-centered computing, which is at the intersection of psychology, machine learning, and signal processing. And it's broadly interested in understanding people in the context of these hybrid human technology systems. So to give a quick example, here's an example from some researchers in 2019 from France, where they're interested in this mental experience, this construct of fatigue. And fatigue among drivers on the road can be really dangerous if people are driving fatigued. So it's better to go over and take a nap. And so these researchers were interested in seeing if they could detect driver fatigue using a variety of different physiologic sensing channels. For example, in this case, using brainwave sensing, muscle sensing, muscle activity sensing, heart rate sensors, and ocular sensors. So this is just an example of the kind of research that we're interested in. So in general, there's some experience that we're trying to understand, and we're trying to train machines to make predictions about those experiences by using different sensed information from the environment or from people. So here's a picture of what I just ended up explaining. So in the middle, this blue box represents mental states and experiences. This is what we're interested in understanding about people. But the problem is we cannot make direct observations about, for example, somebody's level of fatigue, or for students, for example, maybe how engaged they are in a particular lecture in a classroom. But what we can do is make observations about what's going on in the world around people, for example, by monitoring these exogenous changes. And we can also monitor bodily sensations by looking at physiologic information, and we can also look at the different behaviors that people express. And ultimately, we want to train machines to try to make predictions of these experiences, which is really difficult to do unless we have labels of these experiences. So because we can't observe the experiences, we usually ask for people to annotate their own experiences, or we ask for observers to monitor people's behaviors and provide ratings of these different experiences, which we can use for machine learning. And what I think makes this field so interesting is all of the different sources of biases and introspective biases and cognitive biases and all of the stuff that can go on as information sort of travels from your internal mental state to the different behaviors and how it gets perceived and labeled by people. That's what makes research in this field so interesting to me. So here's a picture of what machine learning and human-centered computing looks like. And I'm going to use this picture to ground the rest of the talk. So I do want to point out the different elements here. By the way, I forgot to mention at the beginning, if anyone has a question, feel free to raise your hand or better yet, type it in chat because I'll be sure to see it. I'm happy to take questions in the middle of the talk. Okay, so in research, we start with a participant. And two things happen. So machines need to make observations about these people, for example, using physiologic sensors. And so that could be channels like capturing heart rate and breathing rate and where people are looking, maybe body posture, right? If we're looking at people sitting in chairs, maybe in a classroom. And those observations turn into features. And then moving up from participants, we also have human observers that observe the behaviors of participants while they're doing some particular task, and they rate the construct that we're interested in. So this could be something like stress or anxiety or happiness or engagement, a whole variety of different constructs that we might be interested in. And then these constructs become labels that we plug into a supervised machine learning model, and we train those with the features to generate some predictions of these constructs. And the hope is that these predictions in the future will be based only on the features, and we won't need any of the labels anymore once we have a trained model. So that's the picture we're working with here in human-centered learning. And so I want to ask this question: how do we train the most valid and the most robust learning models for human understanding? And what are the different factors that might make that easy or hard? So let's take a look at some different contexts in which we can collect data that we use in our machine learning models. So we can do studies in a laboratory. We can do them remotely, for example, over Zoom, or we can go out into the wild, as we say, where we go and do studies where people actually are, for example, at work or at home, and collect data there. And in general, the closer to these studies in the wild that we get, the more naturalistic the data is, the more reflective that data is of what actually is going on in the world, and therefore the more valid the results will be to other contexts. So in general, doing research in the wild is a really good way to improve the validity of your studies. And here's some examples of why it's so important to do that. So here are pictures of 6 different basic emotional expressions. This comes from Paul Ekman's work, for anyone that's familiar with Paul Ekman's 6 basic emotions. And over on the right is a picture of Danny DeVito. And so in the left, we may get these images of facial expressions by asking people to look angry or look fearful or look disgusted, for example. And then we get these kind of sort of fake looking expressions. And if you compare, for example, any of these facial expressions to Danny DeVito on the right, you too will probably notice that there's something a bit more genuine about the smile, Danny's smile, and that's actually what we really want to capture. So this is why doing studies in the wild is so important, because we get these really natural behaviors and natural expressions. So here's another interesting example. This comes from a data set called Student Life. In this particular study, researchers were interested in trying to predict the stress levels of students over the course of the semester at different points in time throughout the semester. And so their hypothesis was that maybe stress levels would be predictable by looking at gym activity, or by looking at the workload of students or different deadlines, or whether it's midterm season, for example. They also captured some information from mobile sensing channels. So they had a little app running on student smartphones that would tell them how frequently the students are using their phones. And what they found was, in this context, none of the predictors, gym activity, mood, deadlines, none of these were particularly tied to stress, but they did find a very high correlation between cell phone usage and stress levels. I think that correlation was around 0.8, which is really high on a 0 to 1 scale. So that's really cool. That means there is a signal out there when you're trying to do these studies in the wild. We're able to predict stress, but it's really unfortunate because if you imagine trying to apply that same finding, that cell phone usage is tied to stress to other contexts outside of student learning and a semester, it's just not a robust measure. It's not going to apply sort of necessarily for adults in the workplace or people sitting at home when they're not in school. So here's another quick example. So in a laboratory scenario, there's a particular feature that we can capture by looking at people's heart rates called heart rate variability. And this particular measure has been tied to stress fairly robustly. There's a weak to moderate effect size, where if you have increased heart rate variability, we find people are more calm. And as heart rate variability reduces, we're able to predict stress more reliably. So in a laboratory setting, this is highly reproducible. But when we go out into the wild and we look at heart rate variability, for example, in this work, among different people that are going to work every day, we find that heart rate variability really isn't a robust measure of stress at all. So there's this disconnect, and that's why it's so disconnect between laboratory studies and studies in the wild, and that's why it's so important to be studying people in their natural contexts outside of the lab. So for the rest of the talk, I want to come back to this core question: how might we improve the prediction validity and robustness of our trained machine learning models? And I want to focus on answering that question by looking at these 3 different stages in the machine learning process. So if we look at the data feature stage in the lower left, one way we might improve validity and robustness is by improving the quality of the data that we collect. At the top, another way we might do that is by improving the labels of the constructs that we're interested in measuring. And then ultimately, if we're interested in generalizing the predictions that are output by the machine learning model to other demographics, other cultures, other contexts, we want to make sure that those predictions are appropriately equal in terms of accuracy across different groups of people. And when you start talking about predictive accuracy across different groups, you end up talking about bias and fairness concerns. So if your predictions are unbiased, then they should generalize better to different groups of people. So we're going to talk about each of these in turn, and I'll start by focusing on data quality. So here we conducted this study where we're interested at looking at stress among hospital workers. So if you look at the statistics, hospital workers, especially now after and during the pandemic, are some of the most stressed out workers in America. And even before the COVID pandemic hit, they were they had the highest burnout rate among any of working professionals in the United States. And so in this work, we thought maybe we should be able to detect stress among this kind of work population using environmental, physiologic, and contextual sensing. So we conducted this study that occurred over the course of 10 weeks. So it's a longitudinal slice of data for the same individuals at work and also at home over the course of 10 weeks. And one of the things that we did was to try to assess. So I don't expect you to follow all of these lines here, but I just wanted to illustrate what the link is between the different kinds of information that we can obtain from different sensors and the different kinds of constructs that we were interested in this work. So on the left, you can see the different sensors. These are capturing information about heart rate, breathing rate, where people are, like which rooms they're spending time in the hospital, what the temperature is, how much they're using their phone, whether somebody is speaking nearby or whether you're speaking, but it didn't keep track of what people were saying, just that they were speaking. So all these sources of information are in some way linked to these different kinds of constructs in at least one piece of literature. So each of these lines represents at least one a published work of research that has found a link between the different kinds of features that we extract from the sensors in these constructs. So in this study, we wanted to focus on collecting the most robust and best quality of data that we possibly could to see if improving data quality for these studies that we conduct out in the real world would help us learn, for example, about stress or anxiety or positive or negative affect and these different traits we were interested in. So in this study, we designed this very robust data ingestion pipeline that could take information from the sensors as they're reported in real time and deliver those up to a research server where the data streams were closely monitored. And if anything happened during the study, if any batteries wore down, if any sensors were unplugged, we had staff on site that would immediately go and replace the battery or talk to participants and ask them to put their sensors back on, so that we had the maximum amount of data availability and the highest quality data possible. And also so there's a lot of technical challenges here, of course. But ensuring the success of data quality is not just a technical problem, it's also a social problem. So you need to ensure that the data protocol is incentivizing the participants to continue participating. There's all these different factors that need to be considered, like how comfortable are the different sensors? Are participants willing to wear those every day? Are they actually charging their battery, for example, while they're in the shower so that they can put the sensor back on as soon as they get out? So all of these different concerns come into play when you're trying to create a study to maximize data quality. And here we created a checklist for researchers that are interested in doing these studies in the wild of all these different factors that need to be considered. In our particular study, when we applied all these different techniques, the end result was some of the best longitudinal data of this variety that had been collected with a very low attrition rate. That's a participant dropout rate of less than 4%. And so here's an example of something we were able to do with that data that we may not have been able to do without having a really high data uptime. So in this work, we looked at the movement patterns of different hospital workers in this hospital environment. And we looked at the amount of time that individuals in the hospital are spending in different kinds of rooms. In our study, we looked at laboratories, lounges, medicine rooms, nursing stations, and patient rooms. And by looking at the amount of time they spend in these rooms, we extracted motifs by looking at the room that they're in now, the room that they were in before, and the room that they end up going to next, and looking at how much time, the relative amount of time that they're spending in each of the rooms. So we extracted these motifs, we ran some kind of agglomerative clustering analysis on it, and we came out with these three major clusters that described different kinds of job roles and actually revealed something interesting about how rooms get used. So we did find that each room in the hospital has a unique sort of time usage characteristic. So for example, cluster 2 corresponds the best to these med rooms. So that means the way that people use med rooms is very unique compared to the amount of time that people spend in other sorts of rooms. And that's not particularly shocking, right? We would expect you go to a med room, you get some medicine, and you leave and you deliver it to the patient. But what was really interesting here is we found out that different people with the same job role exhibit the same kind of movement pattern motifs. And so one thought was maybe we could look at deviations in those movement patterns, and that would somehow correlate with well-being or stress reports. Ultimately, that kind of analysis didn't work out. Deviations from these movement patterns weren't very predictive of stress, but that was something we were able to investigate here. We ran this other kind of analysis. So this is a more traditional analysis where we wanted to just try to predict well-being in nurses by using all of the different sources of information that we collected in a hospital. So information like breathing rate, heart rate, everything I talked about before. And you can see from the table at the top by looking at the accuracy column or the F1 column that even when we simplify the well-being prediction problem to a binary prediction problem, are you generally well or are you generally unwell on any particular day, we found the predictive accuracy of a trained model was no better than around 60% on average, which is not particularly impressive. So this 60% is pretty typical for studies that are done out in the wild looking at well-being and stress. And so what we found here is that by improving the quality of our data, we actually weren't really able to drastically improve the validity of the predictions of well-being and stress in this case. So coming back to that big question, how do we improve prediction validity and robustness? So far, we've seen that improving data quality doesn't necessarily give us gains by itself, although that may be sort of a precursor to solving other aspects of this problem if we want to make sure that our predictions are highly accurate predictions for these different constructs. So next, we're going to talk about different ways that we might go about trying to extract better construct labels during this ground truth stage. So here are two examples of different ways that we try to get labels of human experiences. So on the left, you guys may have, any of you may have seen this, for example, at a doctor's office, where maybe you finish with a visit and they ask you to fill out a survey where you have to circle a smiley face or a frowny face and on the top left, and you also have to circle another face showing how intense you are feeling a particular emotion. And then this, for example, would give us a rating of dimensional affect. And that might be useful for assessing the quality of delivered care in a healthcare setting. And over on the right, perhaps in a different context, we're interested in looking at the engagement levels of students. And so we may ask some observers to watch these video clips for, of this student who's watching a video lecture on a computer, and ask the observers to provide ratings of engagement over time. And then we end up with this red signal where the engagement fluctuates over the course as the student is watching the lecture. So these are two different kinds of annotations. And there's actually, in general, sort of 4 different categories of annotations that we can categorize in 2 dimensions. So we have discrete time or continuous time annotations. So discrete time corresponds to moments in time, like right now, we're going to ask you to label an experience. And on the other axis, on the y-axis, is the value. So we could have discrete valued sort of categorical, for example, emotion labels, or we could have continuous, for example, engagement sampling, as we saw in the previous slide. Oh, I see a question here. Question says, can we combine the 2 different kinds of annotations? Perhaps, and yes, some people do try to, yeah, actually, we'll see an example in the coming slide of a continuous annotation being downsampled to a discrete annotation. So we do actually see some crossover here, but in general, during the annotation process, people, at least right now, try to stick to one form of annotation. Great question, though. I'm sure you'll have another question in the next couple of slides. So I would argue that if we're interested in studying people out in the real world and we want to collect the most valid, most robust data possible, that we really need to be collecting these annotations of experience in the same manner that people actually perceive the world. So here's an example. We have a picture of a still frame of David Tennant. And if we were interested in getting an engagement label, we may ask an annotator to look at this picture and assign a label, and that annotator may say, well, he looks kind of tired. But if instead we were to show the whole video clip leading up to that particular frame in continuous time, it actually looks like he's not tired. He's just opening his eyes, he's focused, and we might rate that with a higher level of engagement. I see some other questions here. So let's see, is there a possibility that the data quality didn't improve performance because of the field in which it was implied? Yeah, that's a great question. So I'll come back to that at the end of the talk. So in general, it could be that improving data quality, maybe not in a healthcare setting, may actually improve our ability to generate valid and robust predictions. So far, I don't think it's been demonstrated by researchers in the field. We looked at it just in healthcare. So that sort of addresses the question, but yes, that is still a possibility. And another question here, does continuous annotation have some benefits over discrete annotation? Yeah, and I think I've addressed that here on this slide. All right, so in this particular context, we decided we wanted to try to understand how student engagement evolves over time in a distance learning context. So we asked students to come to a lab and sit down and watch a lecture video. But then after that, we told them to act completely naturally, because again, we want to try to replicate the same sort of, even though it's a laboratory experiment, we don't want to constrain the different actions that people are allowed to do. We want them to act naturally. So we actually gave them food and drink. We told them, take out your notes, eat food and take a nap if you feel like it. And we did actually observe people taking naps during the study, which made it really difficult to assess engagement. And to facilitate this process, we built this experience lab that could ingest all sorts of data. So this video on the left, which I won't actually play because it's kind of loud, shows a keyboard, so we keep track of where the mouse is moving, which buttons they're pushing. This console stream here, this console stream here is showing brainwave data as it's coming in. We captured front-facing video and also a recording of what the students were looking at on the screen. And then this panel on the right has this little slider here, and we asked observers to move the slider up and down to rate the level of engagement over time. So when we do that, we get these engagement traces that look like the red signal up at the top here. And what we found is when we performed regression analysis, or when we tried to train support vector regressors, for example, or random forest regressors, or a variety of traditional learning methods to try to predict engagement from the data we collected, we weren't able to do that. So then we said, okay, what can we do? Let's see if we can downsample this engagement signal and just look at 3 different categories of engagement. So we created this confusion matrix here with 3 different levels of engagement: disengaged, engaged, and highly engaged. And then we found when we trained classifiers to predict the levels of engagement across all of our different subjects in the study, we still weren't able to predict engagement particularly well, which is unfortunate. But if we trained the data on just a tiny fraction of all of the available data that we had for each one individual, and we built a different model for each individual, that model did a very good job of predicting engagement levels over time. So that's this intra-subject confusion matrix here. So, so we did find that, yes, we can sort of predict engagement, but we have to start with a nice continuous annotation, and then we have to downsample it. And this wasn't really a satisfactory answer. So this study started this whole line of research where we were really interested in understanding, are people actually generating good, high quality continuous annotations? So we ran this study here to put annotators to the test. So we asked observers to watch this video of the color green, and we asked them to rate the intensity of changes in green over time. And this video is playing. It's kind of a slow video. I'll skip around here so you can see the shade of green actually does change. And the reason the study was interesting is because now we actually know what the true value of green is, and we should be able to assess how well annotators are actually doing at capturing the variations here. I mentioned that annotators generate these sort of raw annotations, and they look like this newest time picture on the left, where each different colored trace represents a different annotator's opinion about how green changed in this video. And then we go through this process where ultimately we want to end up with some ground truth representation, which is going to serve as our label. That's what we're going to hand off to our machine learning process. So a typical pipeline for turning a collection of raw annotations into ground truth involves some kind of data cleanup. So fixing up any missing values or any sort of data errors that may occur during the annotation process. Then, because different annotators have different reaction times and different lag times, we have to do some kind of temporal alignment of the annotations. Then sometimes when we're collecting annotations in a crowdsourcing environment, for example, there may be some adversarial annotations that really don't correspond to the intended construct we're interested in. So we have to go through this annotation selection step where we try to identify those outliers and remove those adversarial annotations. And then finally, we do some kind of a fusion. So the simplest example of fusion would just be a simple average of the annotations. And then we end up with a ground truth. I have a question here. Was the age or kind of subject the students were watching taking into consideration when explaining certain levels of engagement? How about differentiated engagement levels for single kind of course with diverse participants? Great question. So in this previous example, we were just looking at sort of college age, typical age range of students. So there could be some variation in engagement for different groups. And we didn't actually define engagement. So this is sort of a recurring theme in human-centered computing. When you give a very rigorous definition of what it is that you're interested in measuring, you can get more consistent measurements of that well-defined construct. But that well-defined construct may not correspond necessarily to the way that people actually perceive it if you didn't tell them what exactly you meant. So here we didn't define engagement, we just left it up to each person's subjective assessment. And those are the annotations we got. In this green experiment, I don't think there's really any difference in the way that people fundamentally perceive intensity shifts. So we're hoping that even without defining what we mean by green intensity, people did a good job of capturing that intended ground truth. So we ran this in two different studies, task A and task B, that are shown here. The bold magenta line shows the true intensity shifts of green over time. And again, each of the thin colored traces shows an annotation from a different annotator. And the annotations here obtained a really high agreement. So we don't have any adversarial annotations. Everyone's trying to do a really good job. But I want to point out some interesting things that we do see. So first of all, in this sort of middle region for this task, a lot of the annotations tend to overshoot the intended value. So in truth, the true level of green here sort of stops and flattens out and doesn't change. And a lot of the annotations overshoot that value and then eventually come back down later. The second thing is that there's a failure to annotate that portion of that green change as a constant region. So at that particular moment, green was not changing. And if you look at the different annotators, the shade of green that they're annotating is actually changing during that period of time, which is concerning. And then finally, we also see an inconsistent evaluation of the shade of green at different points in time when we objectively had the same shade of green. Let's see, we have another question here. Can the overshooting be explained by bias? It depends on what kind of bias. I think that's kind of a tricky question to unpack. So maybe I'd like to ask you to save that until the end and we'll come back to it, but that's a good question. Okay, so we given these observations about annotator behavior, we decided to look a little more closely at what it is that annotators are actually doing good at. And here in this work, we looked at annotators' ability to capture the trends in the annotation space. So for each of our 10 annotators on the x-axis, we're plotting the true derivative of the change in green over time. And on the y-axis, we're plotting each annotator's derivative in their own produced annotation. And each point in this plot represents a different frame where we sampled while we were recording the annotation. So you can see these points cluster primarily in quadrants 1 and 3, which means that annotators are by and large doing a great job of capturing the direction of change, right? If it's increasing, they annotate an increase, and if green is decreasing, they annotate that decrease. But they're not doing such a great job at capturing the magnitude of that change. And if we take a look at some other works, so there's this interesting work called The Ordinal Nature of Emotion from Georgios Yannakakis, Carlos Busso, and other collaborators, where they've also found that in various contexts, especially if you go back and you look at sociological evidence, philosophical evidence about how people experience the world, there's this evidence that people fundamentally experience the world in this kind of ordinal fashion, where all of perception and all of experiences are always relative to some previous point in time. And so if that's really true, then it might actually be the case that annotators really are capturing trends well, because that's how they perceive the changes, and they're not actually doing such a good job at capturing the exact values. At this point, I'm also, I do want to finish, so please keep your questions coming, and I'll just come back to those at the end. So now we can come back to this ground truth generation pipeline armed with this question: how do we establish ground truth if we really believe that annotators are capturing trends reliably, but that the values aren't necessarily reliable? So one thing that we might do is, instead of asking people to assign values to things, we might just embrace the ordinal nature of perception and say, okay, let's ask them to just make comparisons. So we might pick two points in time corresponding to two different frames and ask people to look at the shade of green and tell us which one is greener. And then if we wanted to think about how this method might generalize in other contexts, right? This doesn't have to just be the shade of green. We might ask them to compare two images of Einstein, for example, and tell us which one is sillier. So that this kind of comparative annotation is very generalizable. And there's a whole field that focuses on non-metric multidimensional scaling, also called ordinal embedding, which provides this framework for taking comparisons between objects, for example, which frame is greener, and turning that into a metric embedding where each object is embedded in space in a location such that its distance to other points in that space is maximally consistent with all of the comparative observations it uses as input. So I won't get into the math in this talk. I'm happy to address this at the end if anyone has questions. But ordinal embedding is something you can look up. It's a very robust technique. There's different solvers, and here and in this method, we use a particular solver called T-stochastic triplet embedding, which has a few issues, namely it's non-convex, but it turns out with sufficient random restarting and high alpha values in this case, we can do a good job of converging to a local or a global minimum solution. So in this work, we just wanted to do a sanity check. So taking a step back, we're proposing that instead of doing continuous annotations, we're going to extract frames and we're going to ask people to compare those frames. And then we're going to use ordinal embedding to try to reconstruct something that looks like a signal. And so in this work, we actually did that. So we asked people to make comparisons between different frames in this green experiment. And then after computing the ordinal embedding and putting those points back on our timeline, we get something that actually looks an awful lot like the signal, and it correlates very closely with the target signal from which the comparisons were made. So this is evidence that ordinal embedding is a reasonable technique. We might be able to use this to improve the accuracy of our ground truth representations. So now we have this traditional approach where we have these continuous annotations that are good because they afford the annotators this kind of temporal context. And then we have this ordinal approach where instead of asking them to observe the stimulus over time, we're just having them make comparisons between frames, but it turns out we can actually get more accurate results when we do that. But it has this downside that there's no temporal context. Going back to that example of David Tennant, where having that temporal context might be really important. And it's also much more expensive. So, there are many more pairs of comparisons that the annotators would have to make to build an annotation, because if we're doing pairwise comparisons, for example, for each point in our timeline, we need order n squared number of comparisons to generate a robust embedding. So the thought here is there something we can do that merges the benefits of both of these approaches? And in this work, we propose this new pipeline we call perceptual similarity warping, which essentially just stacks the methods one on top of each other. So we start with raw annotations, we fuse them using the traditional annotation pipeline. And then going back to our observation that the trends are annotated very well and that the constant regions are not annotated particularly well, we're going to identify the nearly constant regions of our signal that correspond to the peaks, valleys, and plateaus. And then we're going to use this ordinal embedding technique to try to adjust the locations of those peaks, valleys, and plateaus so that they're more consistent with the truth. And then we apply this sort of, after the ordinal embedding, we apply this linear warping function so that the trends connect to the embedded constant interval regions, and we end up with a continuous looking signal. So it turns out if we do this kind of approach, it works out extremely well. So we can see an improvement of about 0.6 Pearson correlation from 0.9 to 0.96, which is actually huge when you consider the Z transform in correlation space. And so we get really good results. So the key insight here is that this idea of doing iterative annotations is really powerful. So instead of asking for continuous annotations and then just trusting them, if we ask for these continuous annotations, we extract the portions which we don't believe people did a particularly good job on by just partitioning out the trends from the constant regions. We can use ordinal embedding to fix that up using supplemental comparison annotations. So in the next few slides are just some extensions that we've proposed to this basic idea. So one of the things that we need to be able to do if we want to partition out and separate the trends from the nearly constant regions in our annotations is to somehow approximate the annotation signals in a way that makes it easier to identify where those peaks, valleys, and plateaus occur. So in this work, we propose trapezoidal segmented regression, where we use this kind of basis function up here in the upper left, which we call a trapezoidal signal. And in this work, we define that signal as just alternating continuous line segments where every other line segment has exactly 0 slope, and the yellow line segments have non-zero slope. The picture in the lower left shows a trapezoidal segmented regression of those points. So we're fitting a trapezoidal signal with 4 segments there. And in this work, we actually demonstrate that trapezoidal segmented regression has some benefits over total variation denoising, which is the technique that we might use to try to partition the constant regions and annotations out from the trends, if we go back and look at the literature. And here's another method that also leverages the same observation that trends are more reliable. So one of the steps in our annotation pipeline, if we're doing this in a crowdsourcing setting, is one of the questions is how do we identify which annotations are adversarial annotations? And in order to do that, we have to be able to compare the annotations And since we don't know a priori what the ground truth looks like in any problem of interest, we usually identify the outliers by finding ones which don't correspond or don't agree with the majority of the annotations. So here, this is just sort of a toy example in this work. We took these two example annotations that have identical structures when you're looking at the signs of the derivatives, but they're different annotations. And we started with the same assumptions that we observed in the green study. So mathematically, we started from the beginning, and if we define our assumptions mathematically, namely number one, that annotators preserve rank ordering when annotating values, and two, that annotators capture trend directions reliably. And then we turn the crank, we end up with equation 3 at the bottom, which is a representation of how we should be comparing one annotation to another if we want to assess the similarity of those annotations. So using this equation, we defined this sign differential agreement metric, and we compared it to other different ways of measuring agreement for continuous annotations. And we found that for these two signals, which most people would a priori agree are attempts at annotating the same underlying construct, although they do disagree about the value at different points in time. The sign differential agreement metric is the only one that gives us a positive correlation, and all of the other agreement metrics would tell us that one of these is an adversarial annotation. So at this point, I've talked about a variety of techniques that all stem from this fundamental assumption that people annotate trends more reliably. And each one of these methods applies to a different point in this annotation pipeline. So the natural question is, what happens if we put them all together? Can we actually improve the quality of our continuous annotations? So here in this work, we actually do this. We went to Amazon's Mechanical Turk because we wanted to collect adversarial annotations. We wanted to see how well this could do in a really difficult context where we don't have control over the quality of the annotations. So we collected annotations of the perceived level of violence from 5 of the top grossing films from, I believe this is in 2019. These are all Hollywood films. So the dotted red line shows a traditional ground truth estimation where we temporally align and then average the annotations. And the blue trace for each movie is showing what happens if we combine all of our methods and we get that perceptually warped version of the signal where we're using ordinal embedding and everything that we talked about. And then in order to measure the validity of these, we need something to compare it to. And there's a ratings authority called Common Sense Media, which provides ratings of violence for all of basically every movie that comes out. And so we tested different aggregation functions when applied to these two different potential ground truth representations. So we tested min, max, mean, median, and sum. And it turns out regardless of which way you aggregate the ground truths, we end up with the highest correspondence between the CSM ratings authority ratings and the ground truth that we get when we apply all of our techniques together. So now I want to come back to this, this original question. Can we improve the labels and generate better construct labels of these experiences we're interested in? And the answer is yes, that there's some work that we can do here to improve the validity by employing iterative annotation and ordinal embedding techniques. So that's one possible avenue for improving the prediction validity and robustness. And I do want to save some time for questions. I believe this is over at 4:30, so I'll spend a little less time in this last section and save some time to address the questions. But here, so when we look at the modeling prediction stage, the issue of robustness comes up. So if we want to take these, if we want to take our trained machine learning model and apply it in other contexts where we're making predictions on different groups of people or different demographics of people or different cultures of people, we want to make sure that the quality of those predictions is as accurate as possible for different groups of people. So when you start talking about prediction quality in different contexts, you're really talking about machine learning bias, and in some cases, the fairness of machine learning predictions. So when we do that, there's a subfield of psychology called psychometrics that is focused on measuring different traits and attributes and characteristics and skills of people. And that's a very robust field. They've been doing research for decades on measurement and also bias and fairness. So in this work, we pulled some of the years of wisdom out of psychometrics and tried to embed it in the framework of machine-based assessments. So here we illustrate different portions of a machine learning pipeline and which kinds of sources or manifestations of bias are relevant at different stages, or which different kinds of fairness apply at these different stages of the pipeline. And we also went to the computer science literature. And if any of you are familiar with bias and fairness in computing, there's a whole array of different metrics that people use to try to reduce the bias and improve the fairness of these systems. And we mapped each one of those metrics to these different stages during the machine learning process. And actually, I want to talk about automated video interviews, so I'll skip over that. So we conducted this study where we wanted to try to assess the bias of machine learning models that we train on data in a simulated high stakes environment. So here, we wanted to take a look at participants in a study where sort of in the real world now, the way that some Fortune 500 companies go about interviewing and pre-screening resumes is by asking potential applicants for a job to submit videos of themselves answering interview questions. And then a machine learning model will look at those videos and make a decision about whether the company should bother to follow up with those individuals. So this brings up lots of ethics questions, lots of bias and fairness questions, but we wanted to tackle this problem and see if, for example, we could identify sources of bias. So we did a mock study. We had 733 participants record videos of them answering 6 different questions. And then before we did machine learning, in this case, we were interested in looking at perceptions or ratings of hireability. So we had a panel of annotators rate their perceptions, their opinions about the hireability of candidates based on their responses to those questions. And we started with a completely level playing field. So all of the males and all of the females in our data set had equal distributions of hireability, and we also trained the machine learning model on an equal number of males and females. And that was important just to make sure that the inputs to the machine learning process had no evidence of bias. So of course, here we were looking at gender bias as just an example. There are other groups that may be of interest, but this is the one we looked at here. And then we looked at, so here we compared several different measures of accuracy and bias and fairness. So the top 2 plots are showing distributions of accuracy over different participants. And the bottom row of plots is showing distributions of bias measured as a difference in the correlational accuracy between men and women. And the column on the left is showing what happens if we train these machine learning models on features corresponding to different modalities. So for example, verbal modality is what people are saying in their interview. Paraverbal is how they're saying it, and visual features are just facial features and posture features that we extracted from the video. And then on the right side, we tried to mitigate bias using different strategies. So I'll start on the left. So you can actually see that the verbal modality and the combined modalities in the upper left plot both have very similar distributions of accuracy measured by Spearman correlation. And then in the lower left, you can see that the verbal modality has the lowest bias on average compared to any of the distributions. So that's suggesting that most of the meaningful information is contained in the verbal modality, and that if we don't add any of these additional paraverbal or visual modalities, then we're also avoiding adding any bias or additional bias to the machine learning process. And then on the right, we tried different bias mitigation strategies. So here we tried gender norming the features. So we z-normalized the data just within men or just within women. And for the reduced features approach, we tried removing, let's see. Yeah, there's a comment for our CS. Anyway, I'll continue. I'll try and wrap up in just a minute here. So we also tried a strategy where we reduced the number of features to try to eliminate the features that exhibited the most evidence of gender bias. And we found that by removing the features that had evidence of gender bias in them, so features that had different distributions for men and women, we could actually reduce the overall bias in the higher ability predictions. So then if we come back to this overall question, can we improve the robustness and the validity of human-centered machine learning processes? The answer is yes, we can. If we're careful about which features we use when we train our machine learning models, and if we're careful about removing some of the features which exhibit, for example, gender bias, we can improve the robustness of these models. So one interesting place where I think all of this work is headed, and there's some research going into this now, is this issue of feedback. So once we're able to generate highly valid, highly robust predictions of people in real settings with real experiences out in the wild, then we can start to think about how we can use some kind of feedback signal based on the predictions from these machine learning models to try to optimize experience. So for example, if we're talking about optimizing engagement among students in a classroom, these might be reminders to students who are becoming disengaged to re-engage with lecture material. If we're talking about chronic stress in the workforce, this might be a word of encouragement, maybe a notification on a cell phone that says, hey, you're looking kind of stressed, maybe you should take a break, or some other kind of intervention. So I think this is the future. This is where this line of research is heading, but it all hinges on our ability to get these really valid and robust predictors of constructs in different contexts. So I'll end by saying all of this work wouldn't have been possible without a huge amount of effort from many different collaborators from the different universities I've had the privilege of working with. And I'll go ahead and end it there and take questions unless we're out of time. Thank you very much. Let's see. So it looks like Sydney said, go to a separate room at 4:30. So there may be some people that are gone, but for anyone that's still here, I'll go back and try to address some of these questions. It looks like there's just a few. So one question was, how much can you attribute this to default human nature? For example, it might be due to the way that brains perceive colors as opposed to human error. Yeah, that's a great question. So I think that question is applying to the green study. And the question is, maybe these overshooting effects are related to fundamental differences in the way that different brains perceive it. That's also very possible. But if that's actually true, if different brains perceive things differently, and we're also interested in trying to mitigate the impact of these personal biases from any one individual's brain in our annotations, then it's going to be very difficult to mitigate that unless we're collecting lots of annotations from lots of people and averaging those in some way or fusing them in some way to try to average out the errors from any one individual. So I would say, even if it is true, we kind of have to hope that on average, different brains have sort of a zero mean distortion of their perception. And then there was a question about the data of video or interview being available to everyone. Yeah, feel free to send me an email and I can share a link to that with you. It looks like that's it. If there are any other questions, I'd be happy to take them. Otherwise, please feel free to shoot me an email. My email is on this slide. And I'll